Okay, so I'm going to do, what am I going to do? Oh, I skipped something important. Uh, so the next thing that I need to talk about is a force vector naming convention. And you've probably seen this before. It seems uh, it seems like sort of an unnecessarily nitpicky detail right now, but when we talk about Newton's third law, it's going to be clear why we're using this notation. So this is a convention for naming force vectors. And since this is only for naming force vectors, you have to be sure not to use this when you're talking about the scalar variables that represent certain forces. So don't use this for scalar variables. Okay, so the naming convention is we're going to call a force vector F sub AB when we're talking about the force on body A by body B. And to a lot of people, besides being sort of unnecessarily complicated, it also seems sort of backwards with the way you tend to think about things. So get in the habit of thinking the force on A by B, on A by B. Say it. Good. Did everyone say it? Okay. So the force on A by B, if you're talking about the force on B by A, it would be FBA, you know. If you're talking, and those subscripts usually represent something that has to do with the object. So if you're talking about the force on a car by the street, you might, name it FCS. It just something that represents those two objects to you. So for example, say that you had two objects sitting on top of each other. Let's say that this is 20 kilograms. This is 50 kilograms. And let's say that there is a downward force of 100 newtons pushing on the top one. Then a free body diagram of the 20 kilogram box. Okay, so what forces would be acting on this? So there's the 100 newtons. There's the weight. That's straight down with a magnitude of 490.5. And then, yeah, so this, ooh, you know what I should have done? I'm gonna do it now. Let's say that we're also applying a horizontal force here. Let's say this is 50 newtons. And let's say that this is static. Okay, it's not moving. And that means that there's friction between these two, and there's friction between the 50 and the ground. Otherwise, these would be accelerating to the right. Okay. So there must be friction and contact with friction is always represented as an unknown force vector. Okay, so if there's contact with friction, there are two components of force, and we don't know either one of them. Okay, if like you could represent them with a single variable if you knew the coefficient of friction, and that's probably what you did most often in physics. But for now, we don't know the coefficient of friction, and we're just going to assume that there's an unknown force vector applied between these two bodies, and there's an unknown force vector applied between the 50 and the ground. Okay. Okay, so we don't know the direction of the force applied to the 20 by the 50, right? So I'm going to write this as a coordinate system, and I'm going to associate that coordinate system with a vector variable f on the 20 by the 50. So why did I make this the force on the 20 by the 50 instead of the force on the 50 by the 20? It has to do but with which body you're isolating. So in a sense, you can think of it as any forces where you're using this notation, the first subscript is the chosen body, because you're always talking about, you're figuring out the force that's on your isolated object. Oh, and then this other one that I added, there's this 50 Newton force. Okay, and then the free body diagram for the 50 kilogram object. Well, there's the weight. Oh, I did the weight wrong on this one. Yeah, this one should be 196.2. So the weight of the 50 kilogram block should be 490.5. And now we're just going around. No, I'll just assume they're always newtons. You don't have to, I guess, worry about units. You should be clear to yourself on what the units are, but I'm never going to be really paying attention to it. Most of the time, everything's going to be SI units. Okay, so there's the weight. Now we're going around the boundary looking for contact. So where else are there going to be loads? There's going to be a force applied by the ground, and it's not just a normal force, it's two components because there's friction. And so I'm just going to write that as the unknown force vector on the 50 by the ground. And there's also a force applied to the 50 by the 20. That's at the top. So there's going to be another force vector F on the 50 by the 20. Yeah, we just haven't talked about it yet. But yeah, that's exactly right. So this is where you would use Newton's third law. Yeah, so what that's saying is we don't know this component or this component of this vector. No, that's an important question and that's a tricky thing, but to keep that kind of stuff straight, all you're trying to do is go around the boundary that you drew and look for the forces. So apply the weight force, and then just look for the things acting on that boundary. If it's not on that boundary, then it doesn't show up there. So that 100 is up here somewhere, not on the boundary, so it doesn't appear. Yep.
Can you remind me again why we don't know the direction of the normal forces?
Because there's friction. I mean, we do know the direction of the normal force. So remember, the normal force is just the component of that force that's perpendicular to the surface. We do know the direction of that component, but we don't know the relative magnitude of the friction force. And so the combined force vector, we don't know the direction of. You know what I mean? Like we know the normal force is this way. We don't know how big it is. And we know the friction force is this way, but we don't know whether it's this or this, and those would represent two different force vector directions. The normal force is always perpendicular to the surface. That's what normal means. But what we have here is not, it's not quite right to call that a normal force. This is the force vector applied by the ground. It's lumping together the normal force and the friction force.
And the reason we have to do this is because you have that lateral 50.
That's right. We know that if this is in static equilibrium, there has to be a force going to the left to counteract this 50. So
if you didn't have 50, then you could be reversed normal force.
That's right. That's right.
What if you had two 50s pushing opposing direction?
Then if you did that in your head, which in that case it isn't too complicated to do, you could say that the ground contact is only acting up. But any of that kind of stuff that you can do in your head, you also could solve using Newton's second law. So that it wouldn't be critical that you notice that, but if you did notice it, I suppose it could help you skip a step. Any other questions about that one? Okay, so that is, okay, so that's how to use that subscript notation. And now the next thing I want to talk about is the main reason that subscript notation is useful, Newton's third law. So Newton's third law, I'm going to always just abbreviate this N3L. And if you use the subscript notation, this is super easy to... So Newton's third law is the one that says for every action there's an equal and opposite reaction. But that's a pretty... That phrase is very, very easy to misinterpret, So if you're using that subscript notation, mathematically Newton's third law just says this. The force on A by B is equal to negative force on B by A. And that's it. For forces with known directions, Newton's third law says in going to the free body diagram of the second body, I'll give you an example of what I mean by this, but going to the free body diagram of the second body, switch the direction that you draw for the vector, and keep the same scalar variable. So for example, if you have two boxes, and you have 100 Newton force acting on the left of this box, say you know the masses of these, let's call this 30 and yeah, I guess 50. Then the free body diagram of the 30 kilogram box. You have the weight of 294.3. You have, we can assume that all of this is frictionless. You have an upward force, I'll call that the normal force on the 30. You have the 100 Newton force acting. And then you have a force pushing back on the 30 by the 50. Okay, so since we know the direction of this one, we're going to associate this this known direction with a scalar variable. Okay, and since it's a scalar variable, we can't use the subscript notation. Okay, so I'm going to call this something else. I'll call it R or something. Okay, and that's a complete free body diagram for the 30. And now we can go to the 50. So there's a weight of 490.5, an upward force I'll call N50. That's the normal force on the 50. There's some force of the wall pushing on the box, call that F. And now this is where Newton's third law comes into it. The force on the 30 by the 50 is this. So the force on the 50 by the 30 is the same variable in the opposite direction. This is equivalent to the, I guess, the subscript definition. You can see in this case, the force vector, so this direction and this scalar together give you a vector, okay? So the force vector that we could call the force on the 30 by the 50, okay, is equal to, well, what would the components be of this force vector? This R is acting in the negative X direction, right? So this would just be negative R 0. Now this scalar with this direction is the force vector on the 50 by the 30. So here we have a scalar r acting in the positive x direction. So this would be equal to positive r0. Okay. And so this is equal to negative this. Okay. So that subscript notation definition of Newton's third law always holds. It just is sort of cumbersome to deal with when you have forces with known directions. But it's still the same thing. It's just that you can't treat that scalar as the thing with that those subscripts. The problem is that the scalar, a vector is associated with directions. A scalar isn't associated with directions. And you can think of Newton's third law as being a direction thing. You know, it relates force directions. And so how you use your scalars, your directions are totally up to you. And so there's no reason to assume that that the direction rules of Newton's third law are going to apply to however you have these scalars defined. But it does hold for vectors. Okay, that just made it more complicated. But so I'm going to shut up about that for now. But if you're ever, I will say, if you're ever confused about whether Newton's third law applies or not, think about those vectors in terms of those subscripts. You know, Newton's third law only applies when you're switching the subscripts. Like, here's an example. That comes up pretty often. It's like sort of a paradox, sort of a thing that can sometimes be confusing in thinking about Newton's third law. Okay, so say you have this cart full of Raggedy Ann oven mitts. You know, that's how you're making your fortune. Each of these is an oven mitt. And your horse, you're asking your horse to bring these all into town so you can sell them. Fine looking horse. Okay, beautiful. What a horse. Yeah. Okay, so you load up your cart, you tell your horse, head off to town, and the horse is like, wait a minute, I'm not going to do this because as soon as I apply a force to that cart is going to apply an equal and opposite force to me. They're going to counteract each other, and we're not going to go anywhere, you know. So I'm not even going to try. It's a waste of time, you know. Don't you know anything about physics? And but so let me write. So the cart applies an equal and opposite force to the horse, and they can't go anywhere. Well, if you isolate the whole system, so there's the cart There's the horse. What forces act? There's a total weight. There is a contact force. I'll lump all 4 feet's contact forces into one force, but this is the force on the horse by the ground. Okay. And now what about the force on the horse by the cart? And what about the force on the cart by the horse? Well, those are both internal in this free body diagram, so they don't factor into anything. Okay, so for those to show up, you'd have to isolate these 2 things individually. So if you isolate the cart, and I guess you'd have a contact force here too. So you'd have the force on the cart by the ground. So over here, if you isolate the cart, you have the weight of the cart. You have that contact force on the cart by the ground. And now you have this force vector on the cart by the horse. But notice that now when this thing appears, the other one doesn't appear because in this free body diagram, we're only concerned with the forces that are acting on the cart. You know, the force on the horse by the cart isn't a force on the cart, it's a force on the horse. You know what I mean? And so you get the opposite thing if you isolate the horse. Ooh, it's a camel now. So now you have the weight of the horse, the force on the horse by the ground, and back here you have the force on the horse by the cart. And it's true that this is equal and opposite to this, but they don't. You could use Newton's second law to do calculations for any one of these 3, but you wouldn't lump them all together, you know? So you do this one and only one of these forces appears. You do this one, only this force appears. And so those 2 forces don't counteract each other. Any questions about any of that Newton's third law stuff? Okay, so I think you'll have time to finish this problem. I want to give you a problem that you can work on, work together on it, compare answers to each other as you go step by step. And, you know, with 5 minutes left in the class or something, I'll have you stop and I'll work through the problem. And then you'll have a chance to sort of, you can see how well this stuff is making sense to you. You can compare the answers you got to what I got. I think this is a nice way, like I'm going to do this pretty often, because I think it's a nice way to be clear to yourself about where you're getting stuck, if you're getting stuck, you know. Question?
And then, did you say today or tomorrow you're going to tell us?
Oh, yeah, I can tell you right now. I guess I'll post it on D2L, but so let's make the exam on Thursday just about the vector review, free body diagrams for particle statics, and then the particle statics problems. Okay. Okay, so let's say that this block is on the floor. Say there's a 30 Newton force acting to the left. There's a 100 Newton force acting diagonally down and to the right, and that's at an angle of 30 degrees with the horizontal. And there's another force acting down and to the left with a magnitude of 50 newtons. And that makes an angle with the horizontal of 45 degrees. Let's say the box is 20 kilograms. And let's say that the box slides with a constant velocity. And the question is, what's the force vector applied to the floor by the box? It's sliding with a constant velocity. If you calculate the horizontal components of all these forces, they don't equal 0. And so that means that there has to be friction in this. So there has to be friction between the box and the floor. Okay, so see if you can work through that. You're going to start by isolating an object, drawing a free body diagram, and then use Newton's laws. And if you have questions that you can't figure out with the people around you, I'd be happy to answer questions. But this is just sort of a chance to see where you are with this stuff.